everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to look at the electrophilic substitution of aromatic compounds with concentrated nitric acid in the presence of concentrated sulfuric acid, and then a halogen in the presence of a halogen carrier, and then finally a haloalkane or acyl chloride in the presence of a halogen carrier. And this is also called Friedel-Crafts reaction. And we're going to look at its importance to synthesis by formation of a carbon-carbon single bond to an aromatic ring. Then we're going to look at the mechanism of electrophilic substitution in arenes for nitration and halogenation, and to explain the relative resistance to bromination of benzene compared with alkenes in terms of the delocalized electron density of the pi system in benzene compared with the localized electron density of the pi bond in alkenes. And our final learning objective will be to look at the interpretation of unfamiliar electrophilic substitution reactions of aromatic compounds, including prediction of mechanisms. Now we're going to talk about electrophilic substitution. So the delocalized electrons of arenes, so of compounds with the benzene group, have a high electron density and will therefore attract electrophiles. So we get this reaction of electrophilic substitution. Remember that electrophiles are species with a vacancy for a pair of electrons to form a covalent bond. So the general mechanism that we have is that a bond forms between one of the carbon atoms of this arene and the electrophile. And the carbon must use electrons from the delocalized system of the arene, and so this delocalized system is temporarily destroyed. In order to get the stability back, the carbon loses a H+ ion, and the overall result is the substitution of the electrophile. So we substitute a hydrogen for the electrophile. So key things to note are that the delocalized system gets temporarily destroyed, and the carbon loses a H+ ion, and that's what's substituted out. So if we're going to look at a general mechanism of this, for example, I'm going to use benzene. So this is the structure of benzene, and then I'm going to add an electrophile. So electrophiles will normally be positively charged because they've got that vacancy for a pair of electrons. And then what happens is that because we've got a high electron density in the middle of this benzene due to the delocalization of electrons, they are attracted to this electrophile. And so a bond forms between one of the carbons of benzene and the electrophile. So what we get is, again, we draw the hexagon, but this time we're going to have a temporarily destroyed benzene. So the delocalized system is temporarily destroyed. And so on this carbon, we're going to have a hydrogen, and I'm going to attach the electrophile also onto this carbon. And one thing to note is with the first diagram of benzene that I've drawn, obviously we assume that each carbon has one hydrogen attached. So now we're just honing in on one of these carbons that I've attached the electrophile to. And one rule that we need to know is that when we draw a line, a dotted line here, how we've drawn this temporarily destroyed delocalized system, the two ends here and here can't exceed this green line. And so, for example, we could have a hexagon that looked like this. And if you wanted to add the electrophile, say, onto this carbon here, so you draw the hydrogen, and if you wanted to add the electrophile here, we then would draw a green line here, and the C that you're kind of drawing can't exceed this green line. So what we would draw would be something like this, and we'd have the positive. So looking back at our original equation, what happens next is that in order for us to get the stability of the delocalized system back, so to fix the delocalized system, this carbon, which has now attached itself to an electrophile, needs to lose a H+. So it needs to lose the hydrogen that it's attached to. And so what happens is that the electrons from this covalent bond move to this positive charge. And then we get benzene. And then we get benzene, but now with an electrophile attached, and the H plus comes out. Now we're going to look at nitration. So this is the reaction when one of the hydrogens in the benzene ring is substituted by an NO2 group, so nitrogen dioxide. And so we call it an electrophilic substitution reaction. And that's because the attacking group we have is the NO2, and the NO2 acts as an electrophile, and we're substituting one of the hydrogens, so it's a substitution reaction. So the reagents we need are concentrated nitric acid and concentrated sulfuric acid, and the sulfuric acid acts as a catalyst. The condition which we need is 55 degrees Celsius, and this is really important because this prevents further substitution. The electrophile that we're using is this NO2 plus ion, which is also called the nitronium ion. So as an example, we're going to look at the mechanism of the nitration of benzene. So the thing to remember about nitration is that first we need to actually produce the electrophile from concentrated nitric acid and sulfuric acid. So I'm first going to look at the equations for producing the electrophile. This will always be the first step of your mechanism. And so what happens is we have some nitric acid and also some sulfuric acid, and they react together to form H2NO3 plus and HSO4 minus. So why this happens is that the sulfuric acid is a stronger Bronsted-Lowry acid and so that means that it donates a proton or a H plus to the HNO3. So what happens is that H2SO4 is acting as the acid and HNO3 is acting as a Bronsted-Lowry base, so it's accepting a proton. And then what happens in the second step, so this is the first step we have, and then in the second step we have that this H2NO3 plus ion will go on to form this NO2 plus that we're after. This is the electrophile that we're going to use for the substitution reaction, and water. So this is the second step. And what happens here is that H2NO3 plus loses water. And so now we can write an overall equation for the production of the electrophile. So overall, we have that nitric acid added with sulfuric acid. So remember, they both have to be concentrated. They produce HSO4 minus and NO2 plus and water. So again, this NO2 plus is what we call the nitronium ion. And this is what's going to act as the electrophile in the reaction. So now we get on to the actual substitution. So what we have, this is step 2, the electrophilic substitution. So we first draw out a benzene. So we'll have benzene here. And then what we have is the electrophile, which is the NO2 plus. So we have NO2 and I'm going to draw a plus onto the nitrogen. And now if you remember, what happens is that because we have these delocalized electrons in the benzene, this is an area of high electron density, and so it attracts the electrophile. And so delocalized electrons move towards this positive charge of the electrophile of the nitrogen on this nitronium ion. And so now what happens is that we've temporarily broken the delocalized structure. So we still have the outside hexagon of carbon atoms, but now we're going to have this broken delocalized structure inside. So I'm now going to hone in onto this carbon, which I'm attaching this electrophile to, and I've got the hydrogen. And remember that in order for us to fix the delocalized structure, we need to lose a H+. Well, the carbon needs to lose a H+. And so the electrons from this bond move towards the positive charge. And so what we form is we have benzene, but now attached to an NO2. And so this is nitrobenzene. And we also form the H+. And again, this is an electrophilic substitution reaction. So overall, as a balanced equation, including the production of the electrophile and this substitution, what we get is that we have a benzene added with some nitric acid, and we're going to use a sulfuric acid catalyst, concentrated, and the nitric acid is also concentrated, and we also use a temperature of 55 degrees Celsius to prevent further substitution. And what we produce is this nitrobenzene and also water. So again, we need to remember that this is an electrophilic substitution reaction, as the attacking group is an electrophile, it's the NO2, and we're substituting, this NO2 is substituting a hydrogen, and so it's a substitution reaction. And nitration is quite important because it's the first step in the production of explosives, and it's also important in the first step in making amines, which are used to make industrial dyes. So now we're going to look at the halogenation of benzene. So we can react a halogen with benzene if a halogen carrier is present. So we have to have this halogen carrier. And common halogen carriers include aluminium chloride, iron chloride, aluminium bromide, and iron bromide. The halogen carriers are generated in situ. And what we mean by this is that it's generated in the reaction vessel from the metal and the halogen. So the example we're going to look at is the bromination of benzene using iron bromide. So at room temperature and pressure, and in the presence of this halogen carrier, in this example using iron bromide, benzene reacts with bromine in an electrophilic substitution reaction. So what we're doing is we're substituting a hydrogen, so H+ comes out with bromine. So the mechanism actually comes in 3 steps. So step 1 happens because benzene is too stable to react with a non-polar bromine molecule. Because when we think of bromine, we have Br2. But because there's no electronegativity difference between 2 bromine atoms, we don't get a polar bond. And so this isn't a polar molecule. And so we don't have a partially positive charge and a partially negative charge on one of the atoms. So we can't actually do the electrophilic substitution. So what we need to do is actually produce a Br+ ion to react with the benzene instead, because the delocalized section of the benzene inside is attracted to a positive ion. So that's why we need Br+. And this bromonium ion is generated when the halogen carrier reacts with bromine. So this is our step 1, creating this electrophile. So we have bromine reacting with iron bromide, and this will form FeBr4- and also Br+. So we break the covalent bond between the two bromine atoms, and then one of the bromine atoms goes to the FeBr3. So it forms a bond of the FeBr3, and so that becomes a negative ion. And then we get this Br+, and this is our electrophile. And we know that electrophiles are usually positively charged because electrophiles have to have a vacancy for a pair of electrons to be donated to it to form a covalent bond with something else. And so step 2 is where we actually substitute in the electrophile. So the bromonium ion accepts a pair of electrons from the benzene ring to form a dative covalent bond in an electrophilic substitution reaction. So what we have is we have benzene, and then we have the electrophile, which is this Br+. And because of the high electron density, because of the delocalized section of the benzene, these electrons are attracted to this positive charge. And so they move towards this Br+, this electrophile. And now we form an intermediate. So this is exactly like all the other electrophilic substitution reactions that we've seen, all their mechanisms. And so what we have is we have this carbon where it's originally attached to one hydrogen, but now it's also formed a dative covalent bond with this Br+. And now we know that this delocalized system actually gets temporarily destroyed. So we denote this by a C and then having a positive charge. And so the rule is that when we draw a straight line from between the two carbons which are next to the carbon which we've bonded the bromine to, the ends of this delocalized system can't exceed this green line. And so this intermediate is actually very unstable, and so we need to fix this delocalized system. So what happens is that this H+ gets removed. So electrons from this covalent bond move towards this positive charge, and this intermediate breaks down. So then we get benzene, but now attached to this bromine, and we get a H+, which has been substituted out. And so our product is bromobenzene. Again, we don't need a number because there's only one substituent, so it doesn't matter where we place it if someone told us the name bromobenzene. So now we need to remember that it's an electrophilic substitution reaction. And why is because the attacking group is this Br+, which is an electrophile, and we are substituting the hydrogen for this bromine, and so it's a substitution reaction. For step 3, we then have to remember that the halogen carrier is actually a catalyst, and so it doesn't get used up in the reaction, and so we have to regenerate it at the end. So how we do that is we take the H+ we've just formed during the substitution reaction, and so how we do that is take the H+ that we formed from the substitution reaction in step 2. So we have H+, and you're going to react that with the FeBr4- that you formed in step 1 when we generated the electrophile. And then what you can form is FeBr3 and also HBr. And so this here is a catalyst that we've regenerated. And also the reason why we call it a halogen carrier catalyst is because these catalysts contain So now we're going to look at Friedel-Crafts Alkylation. When benzene is reacted with haloalkanes with aluminium chloride as a catalyst, we produce what we call alkyl benzenes. And what these are that we have benzene. This is just an example, but we have benzene, and say it's attached to a CH3. We have methyl benzene. So this is an example of an alkyl benzene. It's just benzene attached to an alkyl group. And the reactions that we see are electrophilic substitution reactions. So from this we know that the attacking group is an electrophile, and the electrophile substitutes for a hydrogen. So the example we're going to look at is the reaction of benzene with chloroethane. So the reagent we're using is chloroethane, and we're using anhydrous aluminium chloride. So anhydrous just means without water. So there's no water present. And the condition is we're going to heat it under reflux. So again, reflux is when we have the condenser straight above the thing we're heating it in. And the electrophile is this CH3CH2+. And the electrophile would differ for different haloalkanes, but for chloroethane, this would be the electrophile. So first we need to form the electrophile, and how we do that is we react the chloroethane with the catalyst. So we have chloroethane, which is CH3, CH2, and then Cl, and we react this with AlCl3, and what we form is the electrophile, so CH3CH2+, and we actually have the positive charge on the carbon. And then what we also form is AlCl4-. So now we can use this electrophile in the substitution for step 2. So we have this electrophile here. So if we had a different haloalkane, so in general we have R and then chlorine. So R can be anything. It can be an ethyl group or a methyl group or anything. So that's the alkyl group. And then chlorine is what we have attached for it to be a haloalkane. Then what we have is that the electrophile is equal to R+. So that's how we get the CH3CH2+. And now what happens is that we get the substitution with the benzene. So what we have is, firstly, we have our benzene, and then we add our electrophile, so this CH3CH2+, and then we can form our ethyl benzene, and also a H+, because we've substituted that out for the ethyl. And so this is ethyl benzene. And the next step we need to do is the regeneration of the catalyst. And it's also really important to remember that this is an electrophilic substitution reaction, because the attacking group is an electrophile, so it's got a vacancy for a pair of electrons to accept to form a covalent bond with something else. And also we are substituting the hydrogen for the ethyl group. And in the final step, we then regenerate the catalyst. So we use the two products, so the two byproducts that we're not actually using, this AlCl4- and this H+. And we're reacting them together to reform the catalyst. So we have AlCl4- reacting with H+, and this forms AlCl3 and HCl. So this here is the catalyst that we're after. The other type of Friedel-Crafts reaction that we can get is Friedel-Crafts Acylation. So this reaction was also discovered by Charles Friedel and James Crafts, and this type of acylation is just like any other acylation reaction that we've seen before. And so what that means is that it introduces an acyl group into another molecule. So as a reminder, the acyl group is this RC double bond O group. And when we react arenes with acyl chlorides and also with an aluminium chloride catalyst, we form aromatic ketones via an electrophilic substitution reaction. And because we're using aluminium chloride as a catalyst, this means that we need to regenerate it at the end. And we know this because catalysts aren't used in the process, so they aren't used up. And so that means that it's always regenerated at the end. So the reagent we're going to be using is an acyl chloride with this aluminium chloride catalyst. And the condition is that we don't have any water to prevent the reaction of aluminium chloride. And the general electrophile that we have is this RC double bond O plus ion. So it looks like this. We have R and then C double bond O plus. So we're going to look at a general reaction. So step one is generating the electrophile. So what we do is react the acyl chloride with the aluminium chloride catalyst. So a general formula for an acyl chloride is RC double bond O Cl. And then we react it with aluminium chloride. And what this forms is our electrophile, so this RC double bond O plus ion, and then also AlCl4 minus. And one really useful thing to know about this AlCl4 minus is that it's actually got a tetrahedral shape, because we have the aluminium in the middle, and then we have the original three chlorines. And then now we have an extra chlorine at the top. But aluminium doesn't have any more lone pairs of electrons to bond with this chlorine. And so both of the electrons in this bond come from the chlorine, and so it's a dative covalent bond. So they're donated to this aluminium. And so this is a negative ion, and it has a tetrahedral shape, because the dative covalent bond classes as a bonding pair. So we have 4 bonding pairs, which repel each other by the same amount. And so the bond angle is also 109.5 degrees. And then in step 2, we get the electrophilic substitution. So we have benzene. And we add it with this electrophile, this RC double bond O plus ion. And then what we form is benzene attached to this C double bond OR. So this is our acyl group. And then also the H plus has been substituted out. And this would be named 1-phenyl. And then some kind of ketone. It depends on the R. So for example, if R was CH3, and the name of it would be 1-phenyl ethanone, because we would have 2 carbons. So this is our aromatic ketone. And then finally, we have the regenerating catalyst step. So we have that the AlCl4 minus ion produced in the first step, so here, reacts with this H plus from the second step to form AlCl3 and HCl. So AlCl3 is our catalyst.